In this tutorial, we're going to cover 3 ways for performing schedule optimization. The first method that we'll cover is an exhaustive search. So this is where we search over all available options. A second one is going to be a heuristic, like Johnson's rule. And then a third is going to be integer programming or mixed integer programming. So we're going to use an optimizer to help us find the solution very quickly by posing it as a mathematical optimization problem. Now, schedule optimization, it maximizes productivity, minimizes costs, and reduces delays. It's widely used in manufacturing, logistics, transportation, construction, and project management, as well as healthcare. By optimizing schedules, organizations allocate resources effectively, improve delivery times, and meet customer demands. And this leads to increased competitiveness and profitability. So let's cover these 3 with a simple example that just helps us explore how scheduling optimization is performed. And I'll use each of these 3 methods. Okay, let's consider this scenario where we have these 5 products right here, P0 through P4. And we have 2 machines. And to make those products, this is the time that it takes to process on that machine. And for the schedule optimization, we want to know what order we put these products in to be able to minimize the delay on the machines. So let's go ahead and first of all just use an exhaustive search. And we'll use Python for this, just enumerating over all of the different options. So we know if we have n values, then we're going to have n factorial different permutations of that schedule. So that's going to be equal to 5 factorial. That's going to be 120 that we need to evaluate. That's going to go very fast for this simple problem. So let's go ahead and do that, but just consider as you get to more complicated problems, likely that number is going to get very large very quickly, exhausting the compute resources to be able to search over all possible permutations. Okay, so I'm just going to open up a Python script here, and let's just go with iteration tools or iter tools. We're going to import permutations. And then we'll also import pandas as well. Okay, and we'll come up with all of the different times. You can see the times down here for machine Y. That's 10, 20, 15, 40, and 8. All right, and then also for machine Z. And we're going to get the keys from these as our products, and then also get a number of products. That's our length. All right, let's go ahead and with our list of permutations for PM and a list of the make span time. So as we go through each of these, we're just going to calculate how long it's going to take us to have that schedule. Okay, so for order in permutations products, so again, we're using this iter tools. Okay, it's going to go through all of these different products in each in a different order. And this automates that for us within the for loop. So we don't need to come up with that ourselves. Okay, we're going to append the order, and we'll look up the time for each step. Okay, we'll do that with ty and tz. And then for I in range, the number of products that we have, that's going to be 5. And we'll just calculate the time on y and then the time on z. Okay, and because you have to put I plus 1 here because it has to finish processing on y first, and then it can process on z. All right, let's go ahead and calculate the make span time. We'll just create another loop here. We need to go out to 6 now. Okay, instead of 5 because there's always going to be that 1 delay because it has to be on machine Y first. All right, we'll append the time, and then let's just sort this. We're going to convert it to a pandas data frame just for sorting. All right, and here we have our make span. And create a new column, and we'll sort by make span, and then just look at the first 10 of that. Okay, so I'm going to close this one and I'll just open this up in IDLE so I can run it. Okay, so you can see it's going to be fairly fast. And so it says to go ahead and do, you have two solutions here that have equivalent make spans. It says 4, 0, 1, 3, 2, and that has a total time of 121 time units. And then here's 4, 2, 0, 1, 3. And you can see some other ones in here that are at 123, so only 2 off, but fairly close. So this was number 97 and number 108 out of 120. All right, so that's our very first one. If you want the code for this, you can just come to the APMonitor website, and I'll just show you where that is. Just come to APMonitor.com, ME575, and this is our engineering optimization course website. If you come down here on the right, down to schedule optimization, number 16, you'll see all of the source code for this. So here's the first one, and we'll also go through another example as well using integer programming. Okay, so I'll also post that in the video description for the link. All right, so that's our very first one. Now let's go ahead and go on to our second one. This one's going to be Johnson's rule, okay, or heuristics. And for every scheduling problem, there likely will be heuristics. Maybe somebody that has developed these rules, that they know the schedule, the constraints, they know how to put things together in an efficient way, and maybe there are some rules or heuristics that you can develop that are going to be customized for that particular scheduling application. All right, so let's go with Johnson's rule. So the rule here is we look for the one with the smallest time span. All right, so that's going to be this 8 right there. We can see that's going to be the smallest. And if it processes on machine Y, then we're going to put it first. Okay, so let's go ahead and do our 8 first. This is going to be product 4. That's going to process first. And then in the next step, it's going to be 18. Okay, so that's to process on Z next. All right, so let's look at our next one. The next highest one is 10. So it doesn't really matter which one we choose here, but let's go ahead and just choose this one, the 10 that's right here. I'll go ahead and change the color so it's a little easier to see. Okay, so there's our 10, and that one is shorter on Y than it is on Z. So let's go ahead and put that one here as well. All right, there's 10, and then we'll have 20 as our next step. And that's going to be product 0. All right, let's do our next one now. And you can see our next one is right here. Here's our 10. So that one is going to be on Z, so we'll put that one last. Okay, so I'm just going to come out here to 10 and then 15, the one right before it. And that's going to be product 2. So we're going to do that one very last. All right, now the next to last one. Okay, so let's look at the next lowest one in this list. And it looks like it's here, the number 20. All right, so it's lower on Y than Z. So let's go ahead and put that at the beginning. Okay, the next available slot at the beginning. And so that's going to be 20 here, and then 30. Okay, so the only one that's left that hasn't been processed yet is the 3. And I'll just go ahead and, okay, there's P3, and that one is going to be 40, and then you can see 25. All right, so there's our schedule right there. And if we look at, the delay or the time, if you calculate all of this, okay, we're going to have delays for certain ones. We're going to add up to 121 for this schedule. Okay, so there you can see the delays for each step and then the total time. So this is Johnson's rule right here. and it's a heuristic. Now, you could develop this. We didn't have to go through all 120 different permutations, as you can see, but it's just going to be limited to very kind of simple cases and simple schedules. Okay, these heuristics might get you most of the way to the optimum, but there might be even something more optimal. Okay, so we want to pose this as an integer programming problem. Okay, so this is going to be our third method that we're going to choose. And let's go ahead and just review linear programming or integer programming. So we have decision variables x, and those are going to be integer values. All right, and we might be subject to some inequality constraints, and also maybe x is greater than or equal to 0. All right, and you typically write integers this way, okay, with n dimensions. Okay, and this can also be a matrix as well. So in this case, we're going to have a matrix of values, and these can either be a 1 or a 0. Okay, so each of those elements can either be a 1 or a 0. So if you're going to process it on that step, then it's going to turn into a 1. So for example, if I had 1 here, then all of the other ones must be 0, because I can't fit 2 products on one machine. And then for the next step, maybe I have a 1 here. Okay, and so on. So for each row, as we add those up, as we sum them up, then each row can only be equal to, summation of each row can only be equal to 1, and the summation of each column can also only be equal to 1. So let's go ahead and just review the constraints for this, and I'll create this in Python as well to be able to solve this type of problem. So let's create our summation here, and this is going to be j equals 0. So j, as we look at this is x and then I comma j, and so the I refers to the rows. All right, and the j refers to the columns. And so I'm going to sum this up over from j equals 0 up to 4. So I want to just look at this first column right here and add those up. And so mathematically I just write that x I comma j. All right, and that equals 1. And then I'll say for all, and that's going to be I equals 0 to 4. Okay, now we also have a constraint that each, the summation, okay, over all of the columns also has to be equal to 1. So down here we're going to have similar summation, okay, and this is going to be I equals 1 to 4, and then we're going to have x I comma j, and that equals 1 for all, and then this is going to be j equals 0 to 4. Okay, so for all of those, these have to sum up to 1, because we don't want to process it again on that machine if we've already processed it once. Okay, so those are 2 constraints that we have. Let's go ahead and just start writing this in Python as we map this out. Okay, so our very first thing we're going to do is import Gekko. It has a mixed integer nonlinear programming solver. It can also solve the mixed integer linear programming. We'll set up y and z, and then we're going to set up our array x of 5 by 5. Okay, we're going to give it an initial value of 0 with a lower bound of 0 and upper bound of 1. We also set integer equals true. So it means it's a binary variable. It can only be 0 or 1, true, false. Okay, whether you process it or don't process it. All right, then we have this constraint we're going to add up. Okay, equals to 1. Now I'm going to, I only want to do one for loop here, so I'm just going to switch the indices. basically it just does the same thing. Okay, the summation in both ways. All right, so there's our first one. Now we've got to calculate time. So let's go ahead and calculate what our time is going to be. And we need to get our time of y. And I'll have an I value there, and that's going to be equal to a summation from j equals 0 to 4 with y, the time for that machine, okay, x I comma j. Now this is going to be for all I equals 0 to 4. Now what this does is when those are 1, then it just basically multiplies it by the time right here. Okay, so it just basically is a time for that step. It's just a way to sum it up so we have our decision variables x, all right, and then we are able to calculate the time. And then we're going to do the same thing for z as well. So time z of I equals summation j equals 0 to 4. All right, and then that's going to be zj and then x I comma j. All right, and then that's going to be for all I equals 0 to 4. Okay, so there's our next one. Let's go and write this one in Python as well. Okay, calculate the times. To process, we're going to calculate that with an array of 5 values. And there's our tz, also 5 values. Now we're going to say time to process on y. Okay, I just created that summation like we just wrote out. And then there's a time to process on z. Okay, so we've created our variables. We've created a couple summations for the rows and the columns to equal 1, and then our times as well. Okay, so let's keep going. We have the other thing, the final thing we need to do is calculate the delay. All right, so our delay is, okay, I is got to be greater than, and then this has got to be tz, and then we're going to have I minus 1, okay, minus ty of I. And then what I'm going to do is create this additional slack variable here. Okay, now the slack variable is so that is non-zero only if the delay would be negative. So it's going to add something here if it would say that the delay could be negative. We don't want the delay to be negative, so d has got to be greater than or equal to 0. And also our slack variables have got to be greater than or equal to 0. So we're only going to use this slack variable if the delay wants to be negative to keep that equation feasible. Okay, so that's going to be the thing that we're going to minimize. We're going to minimize the delay. Okay, so we will minimize this delay value to find the optimal schedule. Okay, so let's come back here to our Python script now. We're going to calculate the delay on z, create a new variable with 5 values, and also our slack variable as well. Now here's our delay equals ty. Okay, that's our initial one. Okay, we got to treat it just a little bit differently because initially our delay right here is just 8. It's just whatever we select for our first one. That's just going to be our delay. Okay, and then our slack variable is also 0 for our first one. Now let's go I1 to 5 now. All right, now this shows us our delay equation with the inequality. And then we're going to minimize the summation of all those d values. And we'll also put a small penalty on the slack variables just to encourage those to be 0 when they can be. All right, and then we'll use solver 1. That's going to be the APMonitor solver, and then we'll solve it. So that's all we need to solve this. We've set it up as a mixed integer programming problem, but let's go ahead and extract the solution and print it out. Okay, so I'm going to show what the values of x are, and I'll print the time on machine Y as well as the time on machine Z. And then let's also print out our delay as well. Okay, so I'll save that, and then let's go ahead and solve it with Python. Okay, so there is the output, and you can see it took about 0.1 seconds to solve it. You can see the objective, that's the delay that we're trying to minimize. Came up with a total delay time of 11. And you can also see that here in the results. It's 8 plus 3, total delay was 11. And let's look at that schedule that it came up with. Okay, so it said to process this, so here's our first one, second, okay, there's our next, and next. So you can see the order that it processed these, and you can see the time on each machine, and then also for Y and Z, and there's our delay as well. Okay, now in solving this, it used a branch and bound approach, and there's also outer approximation that you could use. There are many different linear programming, mixed integer linear programming solvers that you can use. In this case, it's just an integer programming problem. And you can see it found a first integer solution after 8 iterations. And you can see the objective there, 11. It found, the integer solution, basically found the solution after just these 8 iterations. But it had to convince itself that it had found the lowest, and so it continued until it terminated with a successful solution. So it only evaluated 25 of these, not all 120. Now, this becomes even more efficient when you deal with the larger scheduling problems. You might have other constraints as well. So this brings us kind of to the final point. Okay, so we talked about some of these strategies for the schedule optimization, but let's say something happens, like a machine breaks, there's a disruption. Okay, so you have to reschedule with new constraints. And in these cases, the heuristics, the Johnson's rules or others, those are going to fall apart because it's not set up to deal with these extra constraints. Also, the exhaustive approach, unless the schedule is very simple, it won't be able to handle, scheduling with new constraints. You'd have to program all of the different permutations of that, and it can be exhaustive search can take too long. And so a lot of times what you do is you use integer programming and make it flexible with all of these mathematical statements of the constraints. If there's new constraints or things change, or maybe the processing time increased on one machine, you can just put that into your program, rerun the optimization, and then it can produce a new solution that you can then implement. So we've reviewed 3 different approaches for schedule optimization: exhaustive, heuristics, and then also integer programming. I guess one other thing I'll mention is that sometimes the heuristics, they can be used to provide an initial condition for the optimization. And what that does is it gives you, perhaps just an initial value, initial guess value that you can use to then more quickly find an optimal solution, especially if it's an integer solution, and then it can eliminate a lot of the potential other choices that it already knows are not potential solutions. Okay, especially in the branch and bound, it can create these cuts or prune parts of this tree so that you don't have to spend as much time optimizing to find the solution. Okay, well, I hope you've enjoyed this. Again, the website is available there with all of the source code for this. And please leave any comments or questions on the video. Thanks.